Hi, this is going to be a video about the how to, build the Enneacontahedron. It's not on center point when I rotate it, but that has 90 faces. There are 60 of these, let's say, fatter um, rhombi, and then there's 30 of the thinner. And it's a very interesting shape for a number of reasons. Primarily for me, it had to do with seeing Steve Baer's Zone Tool primer somewhere in the mid 80s, and he basically showed that the Enneacontahedron could be broke down into 120 cells. These are called rhombic hexahedra, and they're combinations of these two rhombi, making those 5 different Baer cells. There's 10 A cells, there's 20 B, 30 C, 30 D, and 30 E. So first of all, I'm just going to bring up just a hub here, and I'm going to take the triangle here. Let me change this to a lifelike form so we can see that's a true representation of the Zone Tool hub. Okay, a nice view of it. Let's even get the little chamfers on the openings. But there's 20 of these triangular openings, and that's where these yellow struts come out of. Now, when I deal with this, what I call the parallel projection process, if I show all 20 holes being filled up, well, yeah, that's the 20. There's 20 different directions per se, but I actually say there's 10 because you don't use the opposite length from the other one, so you kind of want to get rid of half of those, so to speak. And there's different ways you can do that. I can try to do it real quick for you. But when you're manufacturing or building the Enneacontahedron through this parallel projection process where you're using these struts, there's more than one way it's done. But what's interesting is it ends up being the same form, the Enneacontahedron, when it's finally done. So there's I'm a little messed up here. I wish I wasn't. So if I do this, if I go make a pentagon here with these dots, see that array, and then I can make the next level here. Oops, missed them all then. Okay. What I'm doing here is just showing that those are the 10 unique directions, so I need to get rid of all these if I really want to show you guys what it looks like. And it doesn't have to be this orientation, but those are our directions. We don't really need these blue pentagons anymore either. But I was showing you how the strut fit inside the hub. So I can tell right now this is going to be a long video. Alright, so just fast forward if you want to go to some other point or whatever. But now let's look real closely at this hub. We'll see that in some instances they're just a rectangular hole apart. And in the other instance they're like from here to here apart. And that's what gives you your 2 different angles that then generate the rhombi for the different on the surface of the Enneacontahedron. Here, sometimes it wants to do that instead. Here is your skinny or thin rhombus. Okay, and then if you go from here to here, this will give you your fat rhombus. So it's really all about picking where you start and how you build it, but you can build it many different ways, but it will end up to be an Enneacontahedron. And like I said, there's the Baer cells, which there's 5 of them, and this is the start of making one of them. I believe it is the C. No, excuse me, the D cell. Okay, we'll get into that on another video. So I'm going to put this away for now. Let's go to the Enneacontahedron. Now, remember I said that there was 10 different directions. I also have a really excellent web page to show you that learned a lot from. It was great to find it. Um, I, I think he goes by some kind of moniker of a Hedron dude or something like that. I can't remember his real name anymore. But long ago, well, not long time ago, maybe 4 or 5 years ago, I talked to him about this page, and he did actually, because I figured out how many Bayer cells were in each of these things, so then he did actually credit me right here. Well, we don't have to go to that, do we? No, we don't want to do that. So anyway, let's go back to his page. So in this parallel projection process, here's the 5 Bayer cells. And these verbals don't work for me on this computer. I don't know why, but here's the A cell, because there's the A right there. And it says there's only one A cell out of the 5 different common things there. This is the B. But what's really cool is he's showing an icosahedron, which is the same as those 20 holes on the hub, but he's showing that these 3 make the acute part of the A cell, and then you do these 3, which is different. I can show each one of these real quickly. And then the C has this combination, which is the one that we were looking at, or were we looking at D? I think we were looking at the D one. That's right. That's the one I was using on this example right here. So it's kind of like those triangles. Those red triangles are showing the different directions. So, oops, somehow I got lost the. Okay, so there's your with 3 axes. When you do the parallel projection process, essentially you're going one step at a time, and that's where I bring up the Pascal's triangle as well. So if I say this is the beginning, this is the first of the row 10 on Pascal's triangle, and this was going to be 1. This is a point, just a point on its own, and let's say it's dimensionless. And I'm talking about right here on this row right here. And then, so the next step is there's 10 different directions that I can go. Oops, I'll move that over just a little bit. There's 10 different directions, and there's one of them. I've made a choice. Okay, and then it's like says there's 45 combinations. Well, that has to do with the different size rhombi, but there's only 2 rhombi that can possibly be generated. It's the acute or the fat or obtuse or the thin and the fat or however you want to call it. So then, once I put out okay, I'm going to backtrack a bit. So if we had 0, which was 1, there's just a point by itself. Then I had 10, so I take one of those choices. Now I have a line. Next I'm going to have area, and I'm going to project out another length. So then I do the paralleling of it, and I have a rhombus. Okay, now that's two-dimensional aerial shape. And then we're going to project out. And once you're going that direction, you got to put every one going that direction. And then we parallel it. Now we have a hexahedron. It looks like I made the A cell. No, I made the C cell. I didn't realize I had that thin there. Thin rhombus. I have 4 fat and 2 thin. Okay, so that I'm not going to get into the A and B cells much more than that. But I just wanted you to understand that process a little bit. And on this page that Hedron dude made, then you see these red markings. So then you go, once you do 4 axes, then you're making, from a hexahedron, you're making a dodecahedron. They're not regular. So then you can make 5 hexahedron, then there's 7 dodecahedron. Here's all the combinations with the, and then you can make, then you can make 8 rhombic icosahedron, and then you can tell, see how the pentagon here is red in the center, and here it's the outer reaches, so they're just opposites. And that kind of makes sense. That's the midway point, by the way, on Pascal's triangle. In this row where it says 252, that's where there's 8 different rhombic icosahedrons. So if we actually put the actual number of different shapes made, it would go 1, 1, 2, because there's 2 different rhombuses, 5 for the 5 different Bayer cells. But notice it says 120, and that's exactly how many Bayer cells make up the rhombic enneacontahedra. Then there's the dodecahedrons are at 210, and then the icosahedrons are at 252, and then it goes back, That's what I noticed, because then this has only 7 different forms as you're making this thing larger and larger. It's getting closer to being an encontahedra. That is what I was really trying to get to before. And then this is tricontahedra at the 7. Nope, the 6 where there's 7 of them. There's tricontahedra. Then this is a 42 rhombus form, and there's only 5, just like there was 5 Bayer cells. And then we have just 2. Remember how there's 2 different sized rhombuses, the fat and the thin? Now we only have 2 combinations. And then we have, at the 9 axes, we have just 1 possible way to then you make the enneacontahedron, which has all 10 axes. And there's the Bayer count, 10, 20, 30, 30, 30 of the A, B, C, D, E. So I think that's pretty fascinating. I'm going to pause this and probably call this part 1. Thanks, bye.